Okay, so welcome everyone again. Attending requests. I have a new room today, so hopefully this will make it easier to read the board this time. I had tried using the same board for video calls before, and it worked, but for some reason yesterday was sub-ideal. So this will surely make it better. Anyway, so I wanted to start with a remark that I should really have made last time, yesterday, but I forgot, which is the role of canonical transformations in classical mechanics and in a in a way in we when we once we quantize the theory using the Weyl relations. Well, in classical mechanics, we only care about preserving the form. Well, we call the canonical transformations symplectomorphisms, and once you now it's easy because you see exactly why. If you introduce the symplectic form, it is manifest that if you have a transformation in which you preserve the symplectic form, you're preserving the forms of the canonical equations, which is how normally it is in the expression canonical transformation is introduced in classical mechanics books. So and that's the only thing that we demand. We don't have any other meaningful conditions of what a canonical transformation counts. And that includes this transformation. For example, that's this the example I gave is this transformation Q to P going to capital Q, capital P. And capital Q is this legible before I continue? Is this legible? Can anyone react with a thumbs up if this is legible, or if I'm having trouble? Oh dear. Okay. Maybe that's because of the light. Okay, let me just remove this bit here on the board. Yeah, that should do it. And then there's another blur area. Really. Yeah. Yeah. Okay. Writing bigger as well it helped. So let me do it. I was hoping I'll have more room on the board, but okay. So let's define Q as the log of P and P EQ. So this is nonlinear, but it's a one-line calculation. If you write dP, capital dP, wedge capital dQ, it's one linear calculation to show that this is the same as little dP wedge little dq. So this is a canonical transformation. Now you may, in the spirit of what we had been discussing, you may point, well, if this is a symmetry of the classical theory, then perhaps this is a symmetry of the quantum theory as well after quantization if we impose Dirac's procedure. But it cannot be, at least not unitarily implemented. And the way to see this is that this operator here is not self-adjoint, right? But if there were a unitary transformation, so that P was U, P, U minus 1, if this is self-adjoint, this is also self-adjoint. So this shows that this cannot be unitarily implemented. So this is a statement, of course, what is spoiling here, and I wanted to make this remark, because if we impose that you're looking for a linear transformation, not only the one that preserves this form, but one that is also linear, then one can use Stone von Neumann's theorem to conclude that they are unitarily equivalent, well, up to a phase. That's the only that's the only degree of freedom that is left. And the way to show this, it's actually a good exercise. But the way to show that, if you think of a linear symplectic map, so you had S sigma. So if we pass of transformation T from S to S, so that sigma of TF, so TG, is sigma of F and G, plus linearity, you can show that this induces, so alpha T on the algebra, so on the W of F is W of TF. And you can show that this preserves Weil's relation. And furthermore, you can show that this is surjective. So these are, none of this is a long calculation, but you can show that this is also surjective. So it is, if you start from a irreducible representation, it will become, you will keep it irreducible and regular. So you UT implementing that by W of F, UT star is that by W of T. So in finite dimensions, of course, this is all in finite dimensions because we are invoking Stone's-von Neumann's theorem. But in finite dimensions, linear symplectromorphisms induce this map in classical physics. But anyway, I wanted to draw the attention that the symmetries are so linearity plays an important role here. Okay, sorry. So this is really a comment that I wanted to make soon after introducing Stone's-von Neumann's theorem, but I completely forgot yesterday. So okay. Anyway, so now I wanted to introduce what we really wanted to talk about today. So we paved the way to introduce the axioms of algebraic quantum field theory. And then, so let me list them, and then I will justify them after I list them. So I want them to feel natural to all of you. So the axioms are, so first of all, there's slightly difference in notation here. Now, if I use F, I'm thinking of a test function on a manifold. So this is the manifold representing space-time. So the axioms are phi 1. Well, this one is easy to understand. So this is linearity of this function F. We really want to say that we want to think of field operators as distributions, operator value distributions. So these are test functions on your manifold. And so this first axiom just saying that, well, it is linear and alpha is a constant number, is a number. So this is just statement of linearity. So this should be, this doesn't require that much justification. So for all complex numbers. The second is the equation of motion, and it is implemented by acting with the equations of motions on F, not on phi, as you would expect, but we're going to justify that in a second. So P here is the field equation. So P here is the field operator. In our case, we are talking about scalar field. And I'll justify that in a second. I mean, you may guess where this is coming from, integration by parts. But if you have sufficient regularity, this is implemented in integration by parts. The third is the reality condition. So phi of F is the same as phi of F. Complex conjugate. So this bar here denotes complex conjugation. And finally, so again, you may have a feel of what this is doing. So this is saying that this is a real field. There are field equations that we need to satisfy. This is linearity. What is missing? Certainly we were missing the canonical commutation relations. And we are going to impose that in this form, and that will, I will justify later. The commutator between two of them. Will be I. I'll define what this E is. And G that. And I'll define what this is. So okay. So let's understand why this is the way it is. Oh, by the way, another example here could be in classical mechanics that's a bit more traditional is the action angle variables. You may have seen this. This is another good example. Anyway, okay, so first of all, why are we doing this? So we are thinking of this. So if you're talking about distributions and you want to know how they work and why they are, well, why do you define things the way we are? The best thing you can do is to think of regular functions, and then and understand what happens at least in that particular case. So that's what we're trying to do is reading these functions phi on f to be seen as an integral on your whole manifold phi of x when it exists as a kernel f of x. Well, integrated on the volume, let me call epsilon, integrating over the volume of the whole manifold. So to justify the equations of motion, well, this is just a constant. So just like let's just look at the box operator, what it does. So if I want to write this, and phi of x, which is the box operator on f, and we can integrate this by parts. So you see that because f is compactly supported, this boundary term we can kill, and this becomes this. So this box operator starts acting on phi, and of course this is just multiplication. So you can think of multiplying on phi instead of multiplying f. So then you understand what this is doing. So when you can write phi as when this distribution is written as such, well, this is integrating on the volume. Well, I forgot to put the volume elements everywhere, but that's it, integrating on the volume. So you see that this is implementing. This is when you can write phi like this. This condition is implementing the field equations on phi, which is what you were used to. So that is a justification for that part. Now, okay, so 3, it doesn't require that much justification, but for that, so let me introduce the symbol, what I mean by that, and why it is advantageous to write like this. Okay, so first of all, what is the symbol E? Well, the symbol E is just this combination, advanced minus retarded green functions, acting on a function, on a test function. If you forgive me, I don't want to erase this right now, so I'm going to erase what I just wrote. So E of f is an advanced green function minus a retarded green function. So this is 0 after the past like outside of the past right cone. This is 0 in the future right cone. And these are all both green functions. So so you can think of that green functions are the inverse of and the box, the P, the equation of motion operator. So because they are both green functions, you can see, well, what I mean that P of F, P of RF is 0. Sorry, it's F, not 0. So E of P, or P or E of, sorry, P of E of F. So you take this minus that, so P of E of F is 0. So E of F, if you get a test function, E of that test function is a solution now. So it's useful to think of this object as a map between test functions and solutions. Let's introduce a symbol for the solutions of the equation of motion. I would say curly S. So that's how we should be thinking about this this map E. And this map E has some nice properties too. For example, it is onto. That is to say that for every solution, we can find a test function, so that solution is E of that test function. So let me write a little bit more details. So E of F is 0. That is if and only if E is of the form P of G for some G for a certain test function G. Well, and so to see that, so to see the implication on this side, we write F as P of G. So AF equals RF equals G, which implies that EF is 0. So that's one side of the implication. And if RF is, well, if E of F is 0, on the other side of the implication, that means that AF is equals a RF. And F is P and PAF. This is the identity again. And then that tells us that F equals P of AF. But that's just the G we are looking for. And that should do it. Yeah, so and the other condition that we want to write, which is quite consequential, is this identity. So let me use okay, I'll have to erase this. To justify this, I need the following identity. So think of psi as a solution now, and F is a test function. So the claim is that the integral of psi F is sigma of EF psi. That's my claim. So to prove this, the first thing is to add an identity here in the middle. So let me put a PA here in the middle. And now let's integrate this. So first of all, these are test functions. So let's choose a region of integration. It's that and for each outside. So let's think of this as a tube, and then we're going to integrate on a tube so that F is 0 to the past of that tube and to the future of that tube. So let's call that we can label those tubes by surface of constant T. We are all talking about globally hyperbolic spacetimes here anyway. So we can label that cleanly as T. Well, otherwise, it's even hard to do classical field theory if you don't have globally hyperbolic spacetimes. So that's not anyway. So let's integrate that on the volume. So it's supposed to be integrated on the whole manifold, but then we just integrate on the tube using the support of F. So we write this as an integral on the tube. Psi P A F. And now we have to say who P is. So let's do that. Let's say who P is. So that is integral mu psi radiant mu about F minus radiant. And integrate by parts again. Psi AF plus AF box psi minus AF mu squared psi. So this part is the equation of motion. So this last two terms is this line on the bottom is 0 because of the equations of motion. Now this term now we integrate by parts. So sorry, we apply Stokes theorems, and so we write this as an integral. And again, this is all advanced. So the advanced is 0 on T2. So we can take this as, so this integral becomes on the surface of T1 constant. So this is an integral on that surface. So then it's the normal acting on this, and this nabla becomes the normal, the derivative in the direction of the normal to the surface. So this becomes integral psi, the normal derivative of AF minus AF, normal derivative of psi, which is almost what we want, except that I have AF instead of EF. But that is fine because RF is 0 on T1. So this is a T1 constant surface that we integrate. So so I can add 0 here, which is R of F. So I add 0 for free. So this is the symplectic product acting on EF. So this is sigma of EF and psi. So we can think of that. So this is kind of the ultimately you're trying to generalize phi of F we are trying to generalize this as a distribution. And so you think of that as this mirrored field, this mirrored against test function. And this is what this is. So we can think of that object itself as this mirrored field, looking at this identity here. So, and again, I'm going to justify why it is advantageous. So just bear with me for now. You may be asking why. It's still not an answer, but we're going to use this identity in a second. I'm going to calculate the Poisson brackets now using this identity. Anyway, so let me do that. So let's look at the Poisson bracket, unless there are any questions, but so, well, recall that that's what we started last time. That was the Poisson bracket was sigma on D f of f1, g phi of f2, sigma acting on it. Now to see what this means, recall that this phi, this derivative here, is acting on this phase space. So this this object on the left side has to be seen as acting on a function phi. And so is this side. So let's write in a little bit more explicit notation that will help us identify who this guy is. So we can interpret that side as d by d epsilon and phi f. I don't want to say phi of f of another function, so I'm putting f underneath. So the notation isn't so complicated. Epsilon times a curly phi, and then take the derivative of epsilon equals 0. Evaluate the derivative of epsilon equals 0. But, so this is t by d epsilon of sigma of ef phi plus epsilon phi, acting on, evaluating on epsilon 0, which is just sigma of ef phi. So this Poisson bracket, well, let's write this as f1, f2, and then let's pass an argument phi, the other symbol for phi, and then this is sigma of e f1 phi, e f2 phi. Now I remove this. Now, so this is a generic argument that I can omit. So I write this commonly as f1 phi f2 sigma of e f1 ef2. But using that ef1 as a solution, this is the integral of e. So because ef1 is, so what I mean is, because ef1 is a solution, I can write this as that use the identity that I just erased. So this is just the product of the two, integrate. So this is just e f2 f1 integrated. So that's what we define by e f1 f2. So that this is with the I in front, because it's the commutator, this is not the Poisson bracket. So that justifies, well, and the identity operator, of course. But that justifies this fourth axiom as the canonical commutation relations, the CCRs. It has an advantage of writing this way. Of course, it's, it might look more, it doesn't, I mean, it's an advantage writing this way. It's no miracle. And I will explain what I mean. Is the following. I'm not putting equal times here. I'm not specifying that I'm imposing the commutations relations at a certain time or a certain surface, initial value surface, and going from that. This have lifting is including in this E form. So this is it's an elegant way of doing that, of course, but when you're going to write this as a symplectic product, the symplectic product needs to be evaluated on a certain surface. So with that caveat, but in any way, this is this way the axioms look very clean, and this is what. So this is defining an algebra that we want to define an algebra. Well, this is an algebra of phis. That's not to say that the algebra will include everything we possibly want to calculate about, or what we want to call it observables. I'm not saying that these are all the observables are and of this form. I'm not saying that, but at least they contain some of these operators. Now, so that's an algebra. I didn't say anything about a state. Now, if I'm doing a quantum theory, I need some states. I don't think I have any more clarifying comments about these axioms, unless there are any questions. I think I'm ready to define what a state is in the algebraic framework. Okay, so the state so in AQFT, like state is a linear functional. State is a linear functional from the algebra to the complex number, so linear. With the property of omega of A star A, non-negative for all A in the algebra, and omega on the other end is equals 1. So this generalizes the idea of, this is generalized the idea of taking expectation values. Because if you have a Fock space type of theory, this omega so omega could be seen as taking the vacuum or the expectation value. Well, not necessarily vacuum, but okay. So this is more generic. Obviously, that's why we made this leap to begin with. That's what we justified yesterday. We spent a fair bit of time justifying this. But if we have, so at this point, we need to be reassured that if I have a regular, if I have a Fock space and I have a state on the Fock space, that state is something like this. And it is, right? So if you take this object, like say omega is a state in Fock space, and so I take this object with the operator A here. So this object becomes this map. It's a map of this property that satisfies these two conditions, and it's linear as well. So this generalizes your Fock space construction. So this is all that is required for you to call it a state. But of course, this is, we won't, this is out of the scope of what we're going to talk about, but it's a separate, I do want to mention this a little bit on Thursday, but not too much effort into this. But again, we're doing quantum field theory, so we want to talk about states that, I can calculate objects like the stress energy tensor. And not all of these states are good enough for that. So there's another condition about renormalization, etc., which is called the Hadamard condition. But anyway, we're not going to talk too much about it, but this is not saying that this is pathology-free state in any way, but this is all you can say. It is also doesn't. So in particular, this construction, you can think of another. So this is a map in Fock space, but if you have a density matrix type of situation, taking the trace of rho times, now let's think of a finite dimensional quantum system, taking the trace of rho times an operator is also defines a linear map satisfying these properties. So that generalizes pure and mixed states in those constants. We can also define pure and mixed states, and we will in this context as well. So anyway, so that's all of that to justify that. Now, Okay, so that's very generic and nice. Now there's a very natural question that arises at this point, which is, okay, now let's say I have that. I have an algebraic quantum field theory. So I have an algebra satisfying those axioms and a state. Can I find a representation? And right, and hopefully the answer is affirmative, and it is. This result comes in the form of the GNS construction, in which we're not going to prove, but at least I'm going to comment on a little bit of that, how the construction works. But I absolutely will state it precisely. So let me do that. So this is called the GNS construction. That's from so this is the Gelfand Sigma zero GNS construction. Given there is a C star algebra. I know I didn't say anything about the C property of a C star algebra. So a star algebra is all we discussed before. A C, you also have to have a norm, and the norm, a nice norm that plays well with the star operator. But again, because I'm not going to prove it, I won't have to talk too much about the C property and a state. And this end is the point that I want to emphasize the most about this statement, and a state omega. There is a representation. There is pi from the algebra to linear, I call it F, acting on a Fock space F, and a unit cyclic vector omega such that omega of A is in the form of pi omega for OA. Well, if you're taking the previous mini course, I suppose you already know what the word cyclic means here. But if you don't, it means that if I take pi of A, so that's just a remark, if I take pi of A acting on omega and a collection of all of those for A's in the algebra, this thing is a dense subspace of F. That's what cyclic means. So this, so that's one property that the vacuum has. Okay, so that's the theorem. Again, we're not going to prove, but at least I wanted to give you a taste of what how the construction works, because it is kind of constructive. Yeah, so there is, yeah, I'll give you an idea how this works. So, and again, the starting point should be, we are given a state, and how are we possibly going to define an inner product? We are after an inner product here. And there is one candidate that won't quite work, but will that's a statement of the GNS presentation. So that we have one candidate of a bilinear. Well, there is a bilinear form that we can define. Like we can define getting two elements of the algebra. We can define this object. Let me use the same conventions. BA for every A and B in the algebra. And this is because of the axiom, this is already non-negative, but it could be zero. And that's exactly the main obstruction that that we need to remedy if we want to prove this theorem. And the idea is to define the collection of all elements of the algebra for which omega of you define K as the set of all elements K in the algebra, such that omega star omega of K star K is zero. So that's the problematic set. And now what we do is that if you multiply any algebra element by K on the right, so if what I'm saying is that if you have an element of K, so what you have to verify is that if you have an element of K, A times K is also an element of K. In other words, K is an ideal of the algebra. And then you can take, well, eventually you're going to take the quotient by K. You take the quotient of the algebra by K to remove this problem. And of course, if you take this quotient, we also need to define that it has to be, it cannot depend on the choice of the representative of the equivalence class. So that's the property that we need to show, so that it doesn't depend on the choice of the representative of the equivalence class. And and then of course, then you have to take the Cauchy completion of that quotient to get it that. So anyway, that's the idea of how this works. And then once you define what the Fock space is, so eventually it's going to be the Cauchy completion of A. You take the quotient by K, and then take the Cauchy completeness of that. That's eventually going to be your Fock space, and then you need to define a representation. And then so that the map of A to F can easily be given by phi of A acting on B, or I should say equivalent class of B, just the product A, the algebra product. And again, you show that this is well defined. So, and then and then omega, the state omega, it corresponds to the identity element of the algebra. And if that's the identity element of the algebra, density is immediate as well, to be seen. Anyway, so that is the statement I wanted to mention. That is, well, you also have to show that that's a norm to preserve the C surround. But anyway, as I said, the spirit of this course, I'm not going to be spending all the energy that is necessary to go into this proof. But I do want to discuss its meaning, and especially why I emphasized the word "and" so much in this statement. So this construction, you have a GNS construction for every state. It's this GNS construction is predicated on your given linear functional omega. different states will lead to different GNS constructions and consequently different representations. So yeah, so that's one to many property. That's the whole point of our conversation since yesterday. So the states that can be reached by this Fock space, by acting, in other words, by what I discussed yesterday is a sequence of creation operators acting on this reference state that we call vacuum, omega. That's what we call a volume. So if I two GNS constructions might not, there's no guarantee that it will be equivalent. So this is unnecessary. So this is absolutely a result that we have to keep in mind. But I wanted to emphasize that the multiple vacua are already in the hypothesis of this theorem. So that's that's what I wanted to say. Okay, so now I wanted to start from another point of view, in which is how we inspired. So that's okay. So that's good. That's a bit of a transition point now, in which I wanted to look closely for how we when you're doing constructions, when you obtain a Fock space from a one particle Hilbert space, what we're doing. I want to pay attention on what we're doing with that, and what properties we really used to make that construction, and that will bring us this will bring us to construction of Fock spaces, and if you're having a same algebra. So this is GNS construction is one pathway from an algebra to a state or reference state, but there are other ways in which we can get to that state, and there is different ways of characterizing the freedoms that we have when choosing this reference state, what we may call the vacuum. And that's what I want to discuss there now. So how this comes about when you're doing physics most of the time. It's as elegant as it is, it's not very common that you come to a problem and you say, oh, here is a very natural state in the algebraic framework. So I've given this linear functional that is positive and one when evaluated at the identity. So that doesn't happen very often. Most often, you were talking about quantization procedures. So we talk about, let's say, we have a black hole and we want to define states that represent its evaporation, or you want to define states that represent a thermal equilibrium, or whatnot. Or in the case of the Arrow effect that we were talking yesterday, we had two natural procedures in which we constructed this one particle Hilbert space. One is what we always do in Minkowski, so that's what we do in any books. We had Poincare symmetry, so we had a nice Fourier transforms and etc. So we define it that way. And there was another one that's associated with its natural to an uniformly accelerated observer. And then we made the whole Hilbert space. We made a Fock space out of one particle Hilbert's of one particle Hilbert space, and that is how we define the vacuum. We say, well, now that we have this set of modes that are somehow privileged, now I define annihilation operators associated with them, and I define and that picks up a state omega. So let's look at that closely and let's see what we're doing when we're doing that procedure. And I started mentioning this yesterday. We are given the Klein-Gordon product that comes from the symplectic product for free, just from well, either the classical theory, it's a way of seeing it, or simply looking at the properties of the differential equations, the conservation, Wronskian relations, etc., from the differential equations, the field equations themselves. So we are given a product that is very natural, which is the Klein-Gordon product. But it's not an inner product because if you look at all the complexified solutions, it fails to be positive. So what we do, instead look at a subspace in which the Klein-Gordon product is positive, and that becomes our Hilbert space. Now, but to make that decomposition, we also needed, and this is going to sound eerily similar to the first mini course you were attending, if you were also attending Ricardo's course before this one. We needed any solution to be in the form. So if you take a solution, we had a solution. So the property was we had S1 plus I S2 plus S2. I'm not put an I in. S1. So both of them being a part of the Hilbert space. So this is a part of Hilbert space, and this was a part of I times that Hilbert space. And in that case, the solutions S1 and S2, well, the Klein-Gordon norm or product was 0. So we use that fact. So let's, in the same spirit, so let's look at a possible abstraction of that and see if what we can do. So I'm looking at what I'm going to start discussing now is our K of the proposition 3.1 from the paper of Kay and Wald in 1991, and I'm going to look at it and I'm going to discuss it. So the plan is discuss it, motivate it, discuss it, look at the proof at least in one particular case, which is the case of pure states, which is a lot easier than the proof from non-pure states, and then look at an example very closely and gain intuition or all of that is doing. So let me write the proposition that we are going to be discussing. And so let's see. So that let S sigma real vector space let's say that we give and let mu be a bilinear positive symmetric form satisfying, and this is an identity, so sigma of 2, so the symplectic is bounded by mu phi 1 mu phi 2 for all phi 1 phi 2 in S. I don't even notice that I'm not even saying that this has to be finite, infinite dimension or anything like that. You have a dynamical system if you wish, and you have that property. Then theorem says that then there is H, a complex Hilbert space. And a real linear map the K map from S to H such that Ks plus IKS is dense in H. Mu of phi1, phi2 equals 2 times the real part of K1, K by 2 in H. So it's H is a Hilbert space, so it comes with an inner product. So that's the inner product I'm talking about. And finally, sigma of phi1, phi2 is 2 times the imaginary part K phi1, K phi2 with an inner product in H. For all, this is for all of this for phi1 and phi2. Okay, so first of all, a convention warning. If you look at K's 1978 paper, or K and Ward, from what I got this proposition for, there is a convention difference. So what I'm writing, what they write, mu, is our mu divided by 2. And there's, well, nothing fancy, but just I think all the equations become simpler if we don't put that 2. So that's just a conventional warning. So just be aware of that when you're comparing this, how I'm writing this this proposition, and all the discussion, subsequent discussion, and when you're reading this from the papers, any of the papers of the reference, with the exception of one, I think. Well, I'm not sure, but be aware of this potential convention difference. So we're going to sketch the proof of this, but before anything else, let's see what this is doing. So this mu, you see that this mu is not very constrained. So that's another way. Where we are going from this? So that's another way of characterizing the freedom that you have in choosing this Fock space construction based on a one-particle Hilbert space. This is, by the way, this is called one-particle Hilbert space structure. So this mu is a different way of characterizing the freedom that we have, the freedom that we've been discussing, and this. You can think of that as the freedom of choosing a bilinear form mu satisfying its properties. This property may look, well, we're going to see what it is. We're going to see exactly what it is. But this is, together with that, so this allows us to get to this property, so that you will eventually think of that mu as specifying the 2-point function of a well, the antisymmetric part is specified by the symplectic part already, so that's but the symmetric part is what this mu is specifying. So if you're looking at quasi-Fourier states, specifying the 2-point functions, same as specifying the state itself. So ultimately, you're thinking of this mu as specifying the vacuum in that one particle construction. So okay, so let's see a sketch of the proof of this theorem. And then we are going to look at a concrete example and study that concrete example in detail. That's the plan. That's how we're going to really understand this proposition. All right. So first of all, we're going to use the non-degeneracy of sigma. So we need to see that this mu defines an inner product. Well, this is good. This is good for real space. So now we only need to show that this is non-degenerate, that mu is non-degenerate. So suppose if you have mu of phi1, 0, then there is well, for all, so we need to, degeneracy means that phi1 and phi2 is 0 for all phi2 in S. There is a typo in my notes here. Then we must have, because of that inequality, then we must have 0, so mu for phi1, mu for phi2. But that has to be larger than phi1 and phi2. But if this is, but that entails that phi1 is 0. So that's the last axiom for defining an inner product. Okay, so now we have this pair, S and mu. What we can do, we can complete it. We complete this, we complete this pair to obtain a set what Killian will call R. Now this R is a Hilbert space now with the same product mu. Well, with the extension of mu. Now if you can look at this is a version of the Ries theorem. In particularly, it's a corollary. So my reference here is the corollary of theorem 2.4 in Reed and Simon, the first volume of Reed and Simon. So there is a corollary of theorem 2.4, which is the Ries representation. It has to do with, again, if this is all finite dimension, this is all obvious, because what are we going to define? Just the existence of operator is just a statement of. Okay, let me write. So the statement is that if B goes from H cross H to C, sesquilinear, and B is bounded by norm of X, norm of Y, there is a unique bounded linear transformation A from H to H such that B of X and Y is AX Y for all X and Y's. Now, of course, this is, again, if think of finite dimensional linear algebra, this is obvious by Rees' lemma, right? Any function of that. So there is a unique vector. So now that define that operator that brings your vector to the vector that comes from the Rees representation. But of course, this is more complicated because we are talking about bounded operators and so on and so forth. And nevertheless, this is still true. This still holds. And I'm not anyway. If you want to see the proof, please look at Reed and Simon. But if we apply this corollary to that sigma that satisfy that inequality that look like Cauchy-Schwarz inequality, this corollary implies that there is a function, there is an operator A from R to R such that sigma defined by sigma of phi 1 phi 2 is sigma 1 phi 1 A phi 2 for that inner product of R, which is mu. But let me write as an R inner product of that. So that defines this unique bounded linear operator A. What could A be? Oh, we love to have an interpretation for A, don't you? Yes, we'll get that. We'll get that. For now, let's just continue for now. You're soon gonna have an interpretation for this A. Okay, now let's see some properties of this A. So first of all, we can use that sigma is antisymmetric, so that tells us this. Well, okay, let me write this. So sigma of phi 2 phi 1 is minus sigma of phi 1 phi 2. That's from the definitions of symplectic forms, but this is what we called phi 2 A of phi 1. Let me keep saying that this is the R in the product. So this is minus phi 1 A of phi 2. But this is real. This is a real. We are all talking about real functions here. So this is a dagger phi 2 phi 1, and reality means that this is minus a phi 2 phi 1. And that equality comes from this equality. So that tells us that for all of this operators, so for all these vectors, so this is a dagger is minus A. And if you recall that, if you talk about the norm of the operators is sup of A phi on phi, well, for phi non-zero, that that inequality, the mu inequality, that really deserves a main name, and perhaps we should call it a K inequality. I don't know if that, well, I don't know, I don't want to credit to, but I know. But anyway, that mu inequality that looks like Cauchy-Schwarz, except that we have sigma, that tells us that a 1 and 1 when it saturates. So the fact that, this means that this A can be extended. So the fact that this is bounded tells us that we can extend this action of A to R. When the equality is saturated, when the inequality is saturated, So when we have phi mu phi 1 equals that sense, what we call saturation of inequality, sigma phi 1 phi 2 squared 1 mu phi 2 or all phi 1 now. So then you take, so that's the case in which this saturation case is the case in which we can study in a lot more detail. It is a lot simpler. The case in which it doesn't saturate, I will just defer to the original paper and the references therein to get to the proof. It's in the appendix A. That's what we're following. So then take phi 2 equals A phi 1. Then mu of phi 1 mu of A phi 1 A phi 1 plus minus mu of A phi 1 A phi 1 squared. So mu of phi plus mu of A phi for all phi. So A preserves the norm. If A preserves a norm, we can use the usual trick that the polarization identity, right? That you can write, you write the inner product between two vectors as sums of norms of other vectors, like x minus y, x plus y, x itself, and y itself. The upshot is to say that if A preserves the norms of phi's, the polarization identity also implies that A preserves any products, all inner products. If A preserves all inner products, this means that A is unitary. So that is A star A is 1. When that happens, we can call A J because it becomes a complex structure. And specifically J, what we call this a complex structure in the sense that AJ, J star J is 1, and J star minus J. Why? Well, you see that if that's the case, J squared has to be minus the identity. So the eigenvalues of J can only be plus or minus I. So that's why we call this as a complex structure. So we can think of J as multiplying by I in this vector space. But in the general case, this is not as nice because A will have a kernel. And that's what complicates everything. So then you have to extend. We want to define for the general case, which again, we are not going to prove, but just to give an idea of how things go, we need to extend J to include the kernel of A. So we have to find a J that commutes with A, and we can use the polar decomposition. So that's, by the way, let me say a few words of this polar decomposition is. If A is a bounded, so it is also in Reed and Simon. There's this, what section is this? It's again the section of bounded operators. It is section 6.9. You can also check that. But there is a partial isometry. So if A is a bounded linear operator, there is a partial isometry. So you can write A as U A. This A, this A is what I'm calling A star A to the 1/2. So something like the magnitude of A, but it doesn't have all the nice properties that we want from yeah. So just be careful. Like the star of, if you take the star of this, and you may think that this is the same as A, this non-guaranteed. So the product isn't A. This bar of AB is not necessarily bar of A times the bar of B. So yeah, so just be careful. And it's U who happens to be a partial isometry. A partial isometry means that if you decompose H into the kernel of U and the orthogonal complement of the kernel of U, then for everyone in the orthogonal complement, this U preserves the norms. So that's what it's meant by a partial isometry. So you can still define that, and then you get, so you find that the product, and then you want this J, so then you get this U behaving as the J that you want, and J being A to the -1 will give you that, what you need. And now, of course, and then we are looking for eventually, so this J or A in the case of pure state, well, I'm gonna mention pure states in a second, but in other words, what we want from this J is to be like complex conjugation that we do in flat space. So we're eventually going to be interested in the subspaces that are eigenvalues. So this has eigenvalues plus or minus I. So we are eventually going to be interested in the subspaces for the eigensubspace of plus I, for example. And then you have to be careful, because there are eigenvalues of J that don't, if you have this relationship like this, there are eigenvalues of this product that aren't eigenvalues of A. And that's, again, this is no mystery. You can even find a counterexample of that in finite dimensions. This is, yeah. Oh, I even have an example here, if you can verify. Like this matrix A, 0, -2, 1, 0 is a counterexample even in, so if you obtain this guy will be this will be off diagonal. Yeah. So there are eigenvalues of that are not eigenvalues of that. So that's just a word of caution. And then, yeah. Anyway, then we complexify this vector space. Then we complexify this R. So we are doubling degrees of freedom, and then we're doubling again. And we define the product, and then we define the product from H such that, well, we could call it H hat. So that you take the inner product, the real part. So you define H hat, complexifying that, we put an inner product phi1, phi2 on H hat. That is phi1, phi2 on R, plus I phi1 J of phi2 on R. So that's how we complexify that. Now, and the key step in the case in which this inequality is not saturated is that this isn't enough. What you need to do now to define this projection K, if you do have this, the projection K is very simple. The projection K that we have is simply the projection in the eigenspace of projected S. So that should be 1/2 of 1 minus ij. That should do it, right? Because, well, first of all, this has to be a projection operator, and it is, because the dagger is itself and its squared is itself. And it has to, if J has eigenvalue plus I, this has to act trivially on J. So that's easy. So if the inequality is saturated, all you needed is project into I subspace. If it's not, then you have to double. You have to take the direct sum of H hat with itself. Define a complex conjugation, and then what this in the first part of this entry, it will act as a projection, and the other part, it will act as putting the complex, what remains from the complex conjugation in that part. And again, and I'm not going to prove that, but I'm going to defer the proof from that. Now, what we want to do is to discuss the role of this second entry here in a very particular case, so that we're going to build an intuition of what this is doing and why we need to double the spaces. Does anybody have any guess at this point? Of course, this is well, if you've seen this before, then you might know. But if you haven't seen this before, this might look very surprising. But even if you studied entangled systems in finite dimensional quantum mechanics, you've already seen a version of that, and that's what I'm going to convince you of now. Yeah. Okay, but before I do so, let me just, we're going to study the example in detail, but this is a pretty important proposition, and you want to see that the characterization is bringing this new characterization of mu's and as the choice. Now, what you should ask yourself at this point, let's say that we already have a Hilbert space and a projection K, a K map. Again, think of the K map as a generalizing the property that, oh dear, my battery is low. That's something I needed. Oof, my battery is dangerously low, so I'll have to relocate. Yeah, okay. Let's relocate very quickly. I apologize for that. Suffering this much. But if you already have a K map and the H, can you find the mu? And the answer is yes. Okay, maybe can we take a 2-minute break? I know. I apologize for that. I'll be back in a second. All right, I do apologize for that. I did not anticipate Zoom was going to drain my battery that fast. So anyway, but I don't have that much I want to say today anyway, but I do want to persuade you that if we already have H and K, we can construct mu. So let's do that. So consider mu phi1, phi2 as 2 times the imaginary part of sigma k phi1, k phi2, which by the way is the same as 2 times the real part of the inner product k phi1, k phi2 in H. Of course, this is looking at all this as extensions. And to see that, so what we can, we can verify, and you can also verify that, you know, this 2 times this product. So you see what this is doing, right? This is, if these are guys in the subspace that we want, so we are saying that the real part of that is the mu, and the symmetric is the mu that we are looking for. So this is all building up into interpreting mu as the 2-point function, as the degree of your freedom of choosing the 2-point function of a quasi-free state, which is, so this is all pointing to that direction, and that's exactly what it is. So k phi1, k phi2 in H is mu phi1, phi2 plus 2 times the imaginary part, real part plus the imaginary part, k phi1, k phi2. But this is the same as minus 2 times the real part of the symplectic k1, k2, k phi1, k phi2, which is sigma minus sigma k phi1, k phi2, minus sigma of k phi1, k phi2, putting the bar complex conjugate to define the real part, which is minus sigma of k phi1 plus k phi1, k phi2 plus k phi2, if all the inner parts are 0, which is the separating property of decay. So this is saying that sigma of k phi1, k phi2 is 0. And so in case phi1 and k phi2, the k phi1, so without the complex conjugation as well. So this is the same as minus sigma of phi1, phi2. So this is k phi1 bar k phi2 inner product in phi. So from that we get to the whole product in k phi1, k phi2. It's in H, it's the real part plus its imaginary part. The real part is mu of phi1, phi2. And the imaginary part is minus I sigma phi1, phi2. This is a very important identity. And now, and if we have that, we can define creation and annihilation of, well, first of all, if you're now right, if you have this inner product written this way, what we should write now is that mu inequality, that Cauchy-Schwarz-like inequality, in terms of the inner product. And that is literally the Cauchy-Schwarz inequality for this case, for after the K-map is applied to that. So let me write that explicitly for you. specifically K norm, H norm of K1, K phi 1, H norm of K phi 2, magnitude of K phi 1, K phi 2 squared, which is so that property is satisfied. And once you have that, so that's the mu inequality that there's a final property that you wanted to verify. That's verified, but this is an intermediate step that's worth pointing out. This is the Cauchy-Schwarz inequality for that Hilbert space. Now, I also wanted to mention that if you have that, if you have this beautiful Hilbert space working as intended, now you can define creation annihilation operators just to connect to how we were seeing. So now if we want to talk about states and vacuums, Vacua, etc. So if you have a mode phi mu, now mu labels different modes or different solutions here. You can first of all make it well behaved, put it you map, project it into K. Then you can take so this is the quantum operator, the quantum field operator, and this will give you the annihilation operator associated with that mode. This is the Klein-Gordon product, by the way. And same for the creation operator. So then you can understand the vacuum coming from this K as the vacuum that we know and love from Fock spaces constructions that you've seen before. Okay, I think this is an excellent stopping point with a few remarks. First of all, I've heard you've learned about standard subspaces. So you may see that this is coming about here as well. Specifically, the zero intersection property comes exactly when you look at when the mu inequality is not saturated. When it is saturated, we don't talk about the standard subspaces here. But if I just wanted to mention that because if you're also taking the Tomita Kezaki mini course, there's an obvious connection there. But anyway, I think this is an excellent stopping point for today. What we're going to do tomorrow, before we continue developing the theory any further, we are going to study the smallest possible standard subspace. We are going to study a two-dimensional phase space, see all this construction playing out there. We're going to have an interpretation of what this A operator is doing, what that direct sum is doing, what the K map is doing. We are going to understand that fully in an example we are very, very comfortable with already. And we're going to study also the purity criterion, in which I didn't mention it before, but I will mention as we develop the example. And hopefully all of that will be clear, and you're going to feel comfortable in talking about using this language in what follows. And then we continue developing the rest of the theory after that. So I'll stop here and take questions. Then no questions. I know this is rather dense, but stick around because this was the part that, we needed to introduce all of this. So we did exactly that. But even if you're confused about all of that, stick around. Tomorrow we are going to see a two-dimensional, two-dimensional phase space example, and you're going to have control of what you're going to feel like you understand what this is, and it's going to not seem so arbitrary. No, arbitrary is not a good word, but different. It's not going to sound so different after tomorrow. So hope you to see you all there, and I'll stop here. Oh, there's a message in the chat. Oh, okay. There, yeah, certainly. Let's stop the recording now. See you tomorrow. Bye.